Welcome to The Explainer. Today we're diving right into the bright, fascinating, and completely invisible mechanics of how everyday things dissolve. We're actually surrounded by this kind of chemistry every single day, often just taking for granted the incredible physical interactions happening right inside our kitchen glasses.
I mean, you know that feeling, right? Have you ever wondered why your fizzy cola loses its bubbles the exact moment you open it, but getting sugar to mix into iced coffee feels like a total chore? It is incredibly frustrating to furiously stir that iced drink for 5 minutes straight, only to take a sip and get a sad, gritty sludge of sugar at the bottom of the cup. Well, there's a very specific mechanical reason for this, and it all comes down to the physics of how substances interact.
Here's a quick look at our agenda for today. First, the basics of solubility. Second, capacity versus dissolving rate. Third, solid accelerators. Fourth, the gas exception. And finally, some real-world applications. Let's get right into it.
Part 1. The basics of solubility. So, at its absolute core, solubility is simply the baseline ability of a substance to dissolve completely in a liquid matrix. It's a fundamental property of matter. But what exactly are those two interacting parts we're talking about here? Well, the basic equation is beautifully simple. You take a solute, which is just the substance being dissolved, like a spoonful of sugar or salt, and you mix it into a solvent, which is the liquid matrix doing the dissolving, like water. Combine them, and you get a beautifully blended, completely homogeneous mixture called a solution. Solute plus solvent equals solution. It's elegant, it's simple, and it literally powers so much of our world. Part 2. Capacity versus dissolving rate. Okay. This is where so many people get tripped up, so we're going to bust a major scientific myth right now. The crucial point here is that we absolutely cannot confuse capacity with kinetics. Capacity is a question of scale, how much solute can dissolve. It's the absolute maximum amount of a solute that a specific solvent can mathematically hold. Kinetics, on the other hand, is a question of time. How fast does it dissolve? It's merely the speed at which the solute gets incorporated into that solvent matrix. Take a look at these visuals side by side to really see the difference. On one side, we have capacity, a beaker physically saturated with as much sugar as it can possibly take. On the other side, check out the timeline. That represents kinetics, the actual speed, moving from rapid dissolving in seconds to incredibly slow dissolving over hours. The thing is, some physical conditions might increase both speed and amount, but they are entirely different mechanical properties. You can actually make something dissolve faster without increasing the total amount the water can hold.
Part 3. Solid accelerators.
Think about this for a second. If you want a sugary drink right now, do you start with boiling hot water or freezing cold ice water? You probably intuitively know the answer from making tea or coffee, but let's actually look at the microscopic mechanics behind why that happens. If we zoom way in to the microscopic level, we can see that heat gives particles higher kinetic energy. When you heat up a solvent, those molecules start moving wildly. These faster-moving solvent molecules collide with the solid solute much more frequently and with significantly greater force. They are literally physically knocking the solid apart faster.
So factor 1 is temperature. Heat is essentially our universal multiplier. For solid solutes, increasing the temperature targets both the speed times the amount. Because of all that high kinetic energy, not only does the solid break down faster, but the hotter solvent can physically hold way more total dissolved solid. This is exactly why you can dissolve a massive amount of sugar in hot tea, but very little in iced tea.
Now, what's genuinely fascinating is how stirring actually works mechanically. It isn't just sloshing water around. It mechanically disperses dissolved particles. See, when a solid sits in water, the liquid immediately touching it fills up with dissolved particles, creating this sort of saturated solvent cloud around it. Stirring physically sweeps that dense cloud away, constantly replacing it with fresh, empty solvent that is ready to attack the solid. That brings us to factor 2, agitation, or stirring. But remember our Mythbuster rule from earlier? Stirring targets speed and speed only. It only changes how fast a solute dissolves, not the maximum capacity the liquid can hold. You could stir a cold glass of water all day long, but once it hits its mathematical capacity, no amount of stirring will force more sugar to dissolve. It is, however, fantastic for taking clumpy powdered juice mix and instantly incorporating it into a pitcher of water. Let's pivot to particle size with another quick question about your morning tea. If you drop a solid, dense sugar cube into your cup versus pouring in the exact same weight of loose, granulated sugar, which one disappears first? Here's the secret. Solvents can only attack the exterior of a solid.
So breaking it into smaller pieces exponentially increases the surface area exposed to the liquid all at once. Notice how the surface area unfolds here. A solid cube only has 6 sides exposed. But when you crush it into hundreds of tiny crystals, the solvent can surround and attack every single one of those crystals simultaneously. So factor 3 is particle size. Just like stirring, crushing the solute into a smaller particle size is purely a kinetic speed accelerator. It targets speed only. It absolutely does not change the absolute capacity of the liquid, but it drastically reduces the time it takes to get there. That's why granulated sugar is always going to beat a sugar cube in a race to dissolve. Part 4, the gas exception. Because gases play by a totally different set of rules. Unlike solids, gas solubility is ruled heavily by atmospheric pressure. Zooming in on the gas molecules, you can see that higher external pressure physically forces and traps extra gas molecules down into the liquid matrix. You literally have to push the gas into the liquid and hold it there. So factor 4 is atmospheric pressure. This literally explains why your drink stays perfectly carbonated while sealed tight in its pressurized bottle. The high pressure targets the total amount of gas the liquid can hold. But the exact moment you twist off that cap, the pressure drops instantly. Without that invisible force pushing down, the liquid's capacity for gas just plummets, and the carbon dioxide violently escapes as bubbles, creating that familiar bubble frenzy. Part 5, real-world applications. All right, here it is, your ultimate optimization cheat sheet. If you want to maximize dissolving speed, you use heat, stirring, and crushing. If you want to maximize the total amount of solids, heat is your universal multiplier. But if you want to maximize gases, pressure strictly commands the board. Notice how temperature does not help gases. In fact, warm soda goes flat much faster than cold soda. And these principles, they are quite literally everywhere. In medicine, pharmaceutical companies crush drugs into fine powders and press them into effervescent tablets to maximize surface area and dissolving speed for rapid absorption in your body. In the culinary arts and brewing, we use optimal thermal extraction to pull the absolute maximum flavor compounds out of coffee beans and soup broths. Even in sanitation, soap works by using chemical bridges to dissolve otherwise insoluble oils so we can wash them away. So the next time you're aggressively stirring sugar into a stubborn iced coffee, or you hear that incredibly satisfying hiss when you open a fresh bottle of sparkling water, stop and ask yourself, how is this invisible chemistry operating right in front of my eyes? If stirring doesn't actually help a cold iced coffee hold more sugar, what other daily rituals are we doing completely wrong just because we can't see the mechanics? Keep exploring, keep observing, and I'll catch you in the next explainer.